Hi guys! So this video is going to help you with today's review that you're going to do for today's lesson, okay? So the review is going to be over dilation, similar figures, translations, reflections, and rotations. It's going to be over all the different kinds of transformations. So let's remember what a transformation is. So essentially we have 4 different kinds of transformations. And when I say transformations, what I mean is something that changes a figure. So transformation means something that changes a figure. Okay, so my first question to you is, what transformation occurred in this graph? So if I take a look at the diagram and the graph and I see that I need to identify which one's the original figure, and the way that I do this is the original figure will always have my regular labels like W, X, Y, Z. My new figure will always have these prime symbols. We call them prime, but they look like little apostrophes. And when I see those little apostrophes, that is my new figure. So what I'm going to do is I'm going to label these. So this is going to be my original figure. And the one with the little apostrophes, that's going to be my new figure. All right, you could also use the highlighter if you want to make sure to accentuate the fact that this one is the new figure. You can always highlight it. Color coding always helps. Now, something that I noticed right away is that the size of the original figure has changed. Okay, so there's only one transformation that changes the size of a figure, and that is a dilation. So remember when we learned about dilations, we can either enlarge or reduce a figure, sort of like the pupil of your eye dilates, it enlarges, and then it reduces. So that's the one way that we can remember what a dilation is like. So this is the only one that changes the size of the figure. The others do not. Like, for example, a translation, that one is a slide, meaning we either slide to the right, left, up, down, or a combination of the two, which is not what happened right here because I know that the size changed. In a translation, the size doesn't change, so I know that one's not it. A reflection is more of a flip, and we can flip a figure across or over the x-axis or flip it across or over the y-axis, and in that case also the size doesn't change, but I know the size changed on this one, so this cannot be it. And then we also have the rotation. Now a rotation is a turn about a center of rotation. So if I turn a figure, once again, I wouldn't change the size of it, I just change the location and the orientation of that figure. So the dilation is the only one that looks like what happened here in this graph right here. Now, since it did change the size, I need to think to myself, did it enlarge or did it reduce? And in this case, I'm going to say this is definitely an example of an enlargement. Okay, so now how do I write an algebraic rule for this? Now, in a dilation, we multiply the original side lengths and coordinates to create a new size, okay? So in order for me to look for that multiplication, I need to find the scale factor. Remember, the scale factor is the number that we multiply by the original to get the new. Now, how do I find the scale factor? I need to go ahead and find, in other words, there was a multiplication that occurred to the original to get the new, and in order for me to figure out what that multiplication is, I need to kind of work backwards. So I need to go ahead and divide new side length divided by original side length, and that is going to give me this scale factor. So let's go ahead and remember, we can use side lengths or we can use coordinates. I personally like to use side lengths. So I'm going to go ahead and count right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in the original, I have a side length of 10. Now let's go ahead and see the new. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the new side length is 15. Now my question is, what number did I multiply times 10 so that I get the 15? And in order for me to figure this out, I'm going to have to do my division. So I'm going to do 15 divided by 10. That was my new side length divided by the original. We're going to go ahead and type that into our calculator. Okay, so 15 divided by 10, enter. So that is our scale factor. Let's go ahead and go back. So I'm going to say scale factor equals 1.5. So that is going to be the number that I multiply by the original to get the new. Let's go ahead and check it out. Let's see if that's true. Let's try multiplying 10 times 1.5. Let's see if it does give us 15. So 10 times 1.5 equals, and we get 15. Yay, we got exactly what we needed to get, which is the number that we multiplied by the original to get the new. Now, how do I write an algebraic rule? Remember, we said that scale factor is always multiplied by the original. So when I write an algebraic rule, what I need to do is always start off with x comma y, and I'm going to indicate what happened to the original to get the new. And in order to get the new, I multiply scale factor times x, comma, scale factor times y. And this right here is my algebraic rule. One way that I can prove this is, for example, I have coordinates right here, which are 6, 4. And my new coordinates over here are 9, 6. So I could say, okay, how does 6, 4 become 9, 6? And the way that they become that is we multiply. So 6 times 1.5 is going to give me a 9, and 4 times 1.5 is going to give me a 6. So that is my algebraic rule for this specific dilation. So in a dilation, we always multiply scale factor times x, scale factor times y. Let's move on to the next one. What transformation occurred in the graph? Once again, the first thing I'm going to do is label my original and label my new. So once again, did the size change? And if the size did change, this is most definitely a dilation. So if the size changed, I need to ask myself, was it enlarged or was it reduced? And in this case, this is a reduction because the new figure is smaller than the original. So although it is still a dilation, it's a little bit different from the previous just because the new one is smaller than the original. But same rules apply. In other words, I still need to go ahead and find the scale factor. I always need to find the scale factor in order for me to write my rule for a dilation. How do I find the scale factor? The same way we did it before. We're going to have to divide new divided by original. So let's see. We can use a side length or we can use coordinates. Side lengths to me is always easier. So I'm going to go ahead and count 1, 2, 3, 4. Now keep in mind, we only count straight up and down or straight across. We never count slanted sides. Okay? So there's a 4 right there, and then I have 1, 2. We have a 2 right there. So once again, I'm asking myself, what number did I multiply by times the original to get the new? And in order for me to figure this out, I'm going to have to find my division of new divided by original. So right here, be careful. The new one is actually the 2, and the original is the 4. Now I could turn this into a decimal, or I could just simply simplify. If I do simplify, I would divide by 2 both top and bottom, and I get 1/2. So that's simplified. That could be my scale factor. If I turn this to a decimal, this is going to be a 0.5. Either one I can go ahead and use. And once again, we found the number that we multiplied times the original to get the new. So 4 times 0.5 will give me a 2. Now my algebraic representation or my rule, I'm going to go ahead and write down x comma y, transform so that we can write it like this, 0.5x comma 0.5y, or it can be x comma y 1/2 x comma 1/2 y. And that is our algebraic rule for dilations. All right, let's move on to the next one. What transformation occurred in this graph? Now this time the size did not change. If the size doesn't change, then it's definitely not a dilation. In this case, what I notice happened, if I pay attention to, let's say for example, A and compare it to A prime, so this right here is my original, and this one over here is my new. then I can see that it was a slide. It went to the left and down. So it went left so many units, and then it went down so many units. So whenever it is a slide, then definitely it is a translation. Now, how did it slide? It slides to the left. 1, 2, 3, 4. Okay. So I'm going to go ahead and write down 4 units left. And what else? If I start where I left off, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 units down. Okay, so if I want to write an algebraic representation for this, I need to explain what happened to the coordinates. So I'm always going to start my algebraic representation as x comma y, and with my little arrow, and then I have to indicate what happened to x and what happened to y. So I'm going to go ahead and write down my coordinates. Original A are at 2, 6. New A is, which we call A prime, is at a -2, -3. So I know that the coordinates changed. Okay, so it was a 2 and now it is a -2. And what happened here is that the x coordinate decreased by 4. 1, 2, 3, 4. Since we went to the left, left affects the x coordinate. So I know that the x decreased by 4. And then I'm going to go ahead and pay attention to what happened to my y coordinates. So my y coordinate was a 6 and now it is a -3. It also decreased. And by how many did it decrease? Well, my y coordinate gets affected whenever I go down. So that's going to be down 9 units. 1, 2, 3, 4, 5, 6, 7, 8, 9. And because the slide was downwards, I know that y is decreasing, and I can see it in my coordinates as well. So what happened to the y coordinate? It also decreased, and it decreased by 9. So that is my algebraic rule for translations. So in a translation, we always either add to the x or subtract from the x, right or left. We add to the y or subtract from the y, up and down. Let's try this next one. So right here we have what transformation occurred in the graph. The size didn't change, so automatically I'm going to go ahead and cancel out dilations. And I can see, if I pay attention to B and B prime, it got flipped. So a flip, this is definitely a reflection. Now, how did it reflect? It reflected over or across the x-axis. Okay, so it flipped across the x-axis. And I can tell that this one right here is my original and this one is my new figure. So definitely it is a flip, so therefore it is a reflection. Now, how did it reflect? Across the x-axis. All right, so if I want to know what happened to these coordinates so that I write my rule, I'm going to say x, y were transformed so that, and I need to explain what happened here. Now, if I notice the original coordinates of B are at -4, 4, the new coordinates of B prime are at -4, -4. So let's take a look at what happened to these coordinates. I can see that the x coordinate stayed the same, but the y coordinate did change to its opposite. So I'm going to say x coordinate stayed the same, y coordinate changed to its opposite. Now, how do I change a number to its opposite? I don't add to it. I don't subtract from it. The only thing that I can use to change a number to its opposite is multiplication, but in this case specifically only to the y coordinate, and specifically only a multiplication of times -1. That is the only way I can change a positive 4 to a negative 4. So I need to multiply positive 4 times a negative 1, and that will become a negative 4. So therefore, if I write my rule, since nothing happened to x, I'm going to write x by itself. But I want to change y to its opposite, so I would do something like negative 1 times y. Now just be careful. Remember, we say we can make the 1 transparent or invisible. So we have our rule right there. So every time that we have a little negative floating sign right there, that really means opposite. So by writing this down, I'm saying nothing happened to x, opposite original y, which is exactly what happened here. All right, you guys, so this is the video that's going to help you for today. So make sure that you go ahead and try to complete the rest of the review. And if you have any questions, please send me a message on Schoology or email me. Thank you.